These are the frequently asked questions from Algebra 2 for section 9.4 day 1. Let's start with number 11 here. It says, find the sum of each finite arithmetic series. And I have a problem. I don't know which number of term 31 is. So just as I've talked about with any arithmetic series before, what we have to do is write a rule. Because if we have that rule, we can find anything that we need to know about an arithmetic series. So I know that the first term is a 1. And I stop for a second and I check to see, well, what are they adding every time here? And they are adding 3. So that's going to be my common difference. So to find any term, we take 1 plus, and then we go ahead and distribute the 3 from the right-hand side and simplify that. We get 3n minus 2. So now the question is, what number term is 31? Well, I'm going to put 31 in here and I'm going to find out, because that's what n is. N is the number of the term. So we would add 2 to both sides, and then we would divide by 3, and it is the 11th term. So now it's time to get to work on that formula. We need the sum of the first 11 terms. You know what, I'm going to go ahead and remind you of the formula before I get started. So we want the sum of the first 11 terms because they wanted us to stop with that 31. And you certainly could put 11 back into this formula and see, yes, it's going to come out to be 31 here. So, number of terms, 11 of them. The first term was a 1, and that 11th term was 31. So, to find the 11th term, we need to take 11 halves times 32. And you could grab a calculator if you want, or you could reduce that 2 with 32, so you're going to get 11 times 16, which is 176. And that's all there is to it. So as I have mentioned, there is the key right there. You know, when you have a formula for an arithmetic series, everything comes pretty easily. So let me go to number 13 and go through the same motions here. So for number 13, I know I'm going to need the rule. And to find any term, the first term is a negative 3. And then I notice that they are consistently adding another negative 3. So that's my common difference. And then I need to distribute from the right-hand side and combine like terms. Works out rather nicely there. And we want to know negative 30, which term is that? So we're going to put a negative 30 over here and just do a very, very little amount of math by dividing both sides by negative 3, and it is the 10th term. So now we have our lovely little formula for the sum of an arithmetic series, and we know that that negative 30 is the 10th term. So that goes in for n. The first term was a negative 3, and the 10th term, the one we were interested in for the last term there, was negative 30. So this will be 5 times negative 3 plus negative 30 is negative 33, and you could certainly just grab a calculator to crank that one out, and that's going to be negative 165 when you do that. Or do it by hand, you know, multiplying by 5 is not a big deal. But either way, we figure out which term it is, and then we can find the sum from there. Number 15 says, write each arithmetic series in summation notation. So if I'm going to write summation notation, I have to have a rule. Once again, I start with that. And I see, hey, they gave me the first term. That's a 4. I can see what the common difference is, or I could use subtraction to find it. 8 minus 4 is 4, but I notice everything's going up by 4 here. And then we would go ahead and distribute from the right. And in the end, the formula is 4n, which makes perfect sense. The first term is 4, the second term is 8, the third term is 12, the fourth is 16, etc. So there's the rule. Now, we write our summation notation, and the rule goes out here. And then we let people know, hey, start with a 1. Put a 1 in there, you're going to get that 4. And then we only need 1, 2, 3, 4, 5 terms. So lower limit, start with a 1, and upper limit, end when you get to the 5. Remember, those are consecutive whole numbers that we have there. So you put a 1 in, then a 2 in, then a 3, then a 4, and then a 5. And that says exactly the same thing as what they have for number 15. So number 17, scroll this up a little bit so you can continue to see that one. Number 17, you're going to need the rule. All right, first term is a 5. And they told me it was arithmetic, so 5 plus 3 will give me 8, and you can see they're just adding 3 every time. And then we'll go ahead and distribute from the right-hand side. And simplify. And that is our rule. So we have a 3n plus 2 over there. And now it's all about, how many terms, how far do we need them to go? Because we know the first term is a 5. And if you put a 1 into our little formula there, you will get 5. But the problem becomes, which term do they need to stop with to get 38? Well, that's what this rule is for. How do you get 38? Well, you put 3 times whatever the term is plus 2. So subtract 2 from both sides and divide by 3, and n is 12. And again, you can put the 12 in there. 3 times 12 is 36, and 36 plus 2 is 38. So use that rule, and let me get that back up here so that you can see that. Use that rule to figure out what term are we ending with. How are we getting that? Then, get back up here because I believe I wanted to do number 19 as well. You probably don't need it by now, but maybe you've noticed I really like these. Working with these formulas is a lot of fun. It's just a lot of logic, You just follow the formulas and do algebra intuition, Your intuition tells you, hey, I just put in the numbers that I have and let's see what's left. So a sub n equals -3 plus n minus 1. And we see that they are going to be adding a -3 every time here. So a sub n equals -3, distribute from the right-hand side, minus 3n plus 3. So a sub n equals a -3n, which makes perfect sense when you look up there. The first term is -3, the second one is -6, etc. So there's our rule. Goes out in front of, I didn't get that really sharp enough there. There we go. Goes out in front. And we are teaching you guys to all start at n equals 1 here. And then we just need to know -30. So we'll put -30 in here as the answer, and we'll see what n would have to be, and that very nicely is 10. So there is our summation notation for that arithmetic series. Again, you can check, put the 1 in there, you'll see that you do get the -3, then put the upper limit in, put the 10 in, you get -30, and you certainly could put, 1, 2, 3, 4, 5, etc. in there. It's going to work. That is going to work. All right, number 57 says, which expression represents the series that we see listed up there? And I noticed right away, problem. They are not starting with 1. Cheaters. Well, you can do that. You can start with whatever number you want. We're teaching you a formula method to do this, and so that formula is based on using that first term. So what we would want to do here is just look at a couple of these and see, would they really generate that first term of 14? Because if you can't even get 14 out of there for the first term, you know that's not the right answer. So I look at A, and I figure out, if I put a 2 in there, 7 times 2 is 14, and 14 minus 1 is 13. That's not it. Go over to B. Put a 3 in here. 6 times 3 is 18. 18 minus 4 is 14, so that's a possibility. Let's go to C. 6 times 3 is 18, and 18 minus 4 is 14. Well, then let's go to D. If I put an 8 up here, 8 plus 6 is 14. So those are possibles. Now, the last number that they give me, that upper limit, has to give me 50. So I'm going to check and see, do any of these give me that 50 at the end? Well, 9 times 6 is 54, and 54 minus 4 is 50. So this is still in the running. We go to C. 8 times 6 is 48. 48 minus 4, nope, that's 44. That's not 50. That's not going to give us the right number. And D, if we put that 14 in there, 14 plus 6 is 20, not 50. So that's out. So by a process of elimination, even though they didn't write it the way we would write it, you know, using n equals 1 for the first term, that should generate them, and you can always check, put a 4 in. 6 times 4 is 24, 24 minus 4 is 20, put a 3 in, or I'm sorry, put a 5 in, a 6 in, etc., and it will generate what you need up there. Then, oh, number 58 I wasn't going to do with you. It says, what is the common ratio? Remember, to find the common ratio, just take any term and divide it by the previous term. If they tell you it's geometric, that's all you have to do. Number 59 says, which expression is not equivalent to, and you guys can't see that because that is too high. There we go. Which expression is not equivalent to the fourth root of 4n squared? Well, the first thing that I don't like about this is using a base of 4, because you can use a better base for that, a smaller base, and that's 2 squared. So now I look at this and I'm thinking, wait a minute, that can be simplified, because a fourth root is the same thing as a 1/4 power. So that would give me 2 times 1/4 is 1/2, so 2 to the 1/2, 2 times 1/4 is going to give me 1/2. So this is really the same thing as the square root of 2n. So let's see what's going on up here, because we notice we do have some stuff with absolute value bars up here, but they want to know which one of these is not equivalent to the fourth root of n squared. And as I was doing the problem right there for number 59, that was the process that I was going through with you, but by using that base of 2, we could simplify this a little bit further. Now I go to B, and I see, wait a minute, 2. 2 is supposed to be to the 1/2 power. If they don't put parentheses around that, that's wrong, because powers only go to the closest thing immediately to their left. So this is out, but whenever it's multiple choice, you want to keep going. And C says we could do 2 times the absolute value of n, and that would be to the 1/2 power. Well, yeah, I mean, we're going to need n to be positive in order to take the square root in the end. And D is actually saying, all right, 1/2 power is square root. And yes, we would need that to have absolute value so that we could go ahead and actually find the result and not have to say that it's imaginary. 60 says the graph shows the inverse of which function? So think in inverses right away, and how inverses have to be a reflection over the line y equals x. So that means my graph had to look something like that. So I'm looking at that and I'm thinking, well, f is out because x to the first, that's a straight line. That is not going to happen here. And then I notice that my inverse of this actually gives me a key to what numbers I would need. So as I go over and find just a nice point on this graph, I notice that the graph is at 3, 1. And I remember that when you're doing inverses, and actually I should put that the other way, those two get reversed. So that means one of these 3 remaining equations, when I put a 1 into it, has to give me a 3. So looking at G, that one had a negative 3, so I know that one's out anyway. You know, I don't even bother checking that one. I go to H, 3 to the first would give me 3, so that one's working. This one, if I put a 1 in, it's going to be 2 to the third, which is 8. Well, that's not 3. That's not going to work. It has to be H. It has to be its inverse. So 2 pieces to help us there. Think of the visual of inverses. And the visual of inverses is always going to be reflecting it over the line y equals x. And then how do you generate those numbers? How do you get those? Well, the domain and the range always flip-flop when you're talking about inverses, so you can work your way backwards. Now, 61, love these. Solve the equation by completing the square. So what that means is they want us to get a binomial squared on one side, which means we need a perfect square trinomial. And what that tells me is that this 40 that I see here, it's not helping me. Because if this 40 were the perfect square that I needed for the situation, then I wouldn't have to use this process of completing the square. So what I'm going to do is I'm going to subtract it from both sides. Just get it out of my way so that I can go through the process of completing the square. And 5 minus 40 will be negative 35. Now I want to find the number that will make this a perfect square trinomial. And that's just a little formula here, b over 2 squared. So it's 10 over 2 squared, which is 5 squared, which is 25. So I need to add 25 to both sides. And of course, negative 35 plus 25 will be negative 10. Now, on the left-hand side, I have a perfect square trinomial. So I just think, all right, well, x times x will give me x squared. Something times something will multiply to 25 and add to 10. That something is 5. That's this little b over 2 piece that we did here. And then we take the square root of both sides. So x plus 5 would equal plus or minus I square roots of 10. And then we would have to subtract 5 from both sides. So x equals negative 5 plus or minus I square roots of 10. That's a blast from the past. I like that problem. That's really, really good review for us here. All right. Next one up here, write an explicit formula for each geometric sequence, then find the first 3 terms. Well, to write a geometric sequence, all we need is the first term and r, and that's exactly what they gave us. So the first term is a 1, and r is a 2, and the 1 really doesn't need to be there, so if we pretty this up a little bit by simplifying it, it's just 2 to the n minus 1, that's it. And they want the first 3 terms. Well, the first term was a 1. And if we know that common ratio is 2, that means all we have to do is think recursively here and say 1 times 2 is 2, 2 times 2 is 4, and get those terms. So be thinking that way as you work through the last of these.